An image from a microscope reveals how the two metals, copper alloy and Inconel, mix and interlock to form a strong bond created by the innovative 3D printing process during manufacturing of the igniter prototype. Credit NASA. Judy Schneider. Engineers at NASA's Marshall Space Flight Center in Huntsville, Alabama, tested NASA's first 3D printed rocket engine prototype part made of two different metal alloys through an innovative advanced manufacturing process. NASA has been making and evaluating durable 3D printed rocket parts made of one metal, but the technique of 3D printing, or additive manufacturing, with more than one metal is more difficult. It is a technological achievement to 3D print and test rocket components made with two different alloys, said Preston Jones, director of the Engineering Directorate at Marshall. This process could reduce future rocket engine costs by up to a third and manufacturing time by 50%. Engineers at Marshall, led by senior engineer Robin Osborne, of ERC Incorporated of Huntsville, Alabama, supporting Marshall's engine components development and technology branch, low-pressure hot fire tested the prototype more than 30 times during July to demonstrate the functionality of the igniter. The prototype, built by a commercial vendor, was then cut up by University of Alabama and Huntsville researchers who examined images of the bimetallic interface through a microscope. The results showed the two metals had interfused, a phenomenon that helps create a strong bond. A rocket engine igniter is used to initiate an engine start sequence and is one of many complex parts made of many different materials. In traditional manufacturing, igniters are built using a process called brazing, which joins two types of metals by melting a filler metal into a joint, creating a bimetallic component. The brazing process requires a significant amount of manual labor, leading to higher costs and longer manufacturing time. Majid Babai Center, Advanced Manufacturing Chief at NASA's Marshall Space Flight Center in Huntsville, Alabama, along with Dr. Judy Schneider, Mechanical and Aerospace Engineering Professor at the University of Alabama in Huntsville, and graduate students Chris Hill and Ryan Anderson, examine a cross-section of the prototype rocket engine igniter created by an innovative bimetallic 3D printing advanced manufacturing process under a microscope. Credit NASA's summit given eliminating the brazing process and having bimetallic parts built in a single machine not only decreases cost and manufacturing time, but it also decreases risk by increasing reliability, said Majid Babai, Advanced Manufacturing Chief, and lead for the project in Marshall's Materials and Processes Laboratory. By diffusing the two materials together through this process, a bond is generated internally with the two materials, and any hard transition is eliminated that could cause the component to crack under the enormous forces and temperature gradient of space travel. For this prototype igniter, the two metals, a copper alloy and Inconel, were joined together using a unique hybrid 3D printing process called automated blown powder laser deposition. The prototype igniter was made as one single part instead of four distinct parts that were brazed and welded together in the past. This bimetallic part was created during a single build process by using a hybrid machine made by DMG Mori in Hoffman Estates, Illinois. The new machine integrated 3D printing and computer numerical control machining capabilities to make the prototype igniter. While the igniter is a relatively small component at only 10 inches tall and 7 inches at its widest diameter, this new technology allows a much larger part to be made and enables the part's interior to be machined during manufacturing, something other machines cannot do. This is similar to building a ship inside a bottle, where the exterior of the part is the bottle enclosing a detailed, complex ship with invisible details inside. The hybrid process can freely alternate between free-form 3D printing and machining within the part before the exterior is finished and closed off. We're encouraged about what this new advanced manufacturing technology could do for the Space Launch System program in the future, said Steve Wofford, manager for the SLS Liquid Engines office at Marshall. In next-generation rocket engines, we aspire to create larger, more complex flight components through 3D printing techniques. Explore further. Sparks fly as NASA pushes the limits of 3D printing technology.